Hello everyone. The topic for today is digital to analog converters R2R ladder DAC. Myself, Mrs. Aparna More from PES Modern College of Engineering. I will be discussing today about R2R ladder DAC. In the previous video, I had discussed about binary weighted DAC. So today we will be discussing about R2R ladder DAC. Before that, we will see what is data converters. Data converters is it converts one form of data to the other, like it will convert a digital form of data to analog and an analog to a digital. Your data converters is classified into two types, that is D to A converters and A to D converters. Digital to analog converter is further classified into binary weighted register DAC and R2R ladder DAC, whereas analog to digital converter is classified into flash type ADC, counter type ADC, single and dual slope ADC, and successive approximation type ADC. This is the block diagram of D to A converter wherein we have the reference voltage. Then these are the digital inputs. They are binary inputs. B1, B2, B3, B4. B1 is the MSB, B4 is the LSB, and they are converted into an analog output voltage VO. So the digital input bits are converted into an analog output voltage. We will discuss 2-bit binary R2R ladder DAC. Here, this R2R ladder DAC consists of R and 2R. They are two types of resistors. Like for example, if R is 10 kilo ohm, then 2R is 20 kilo ohm. There are binary switches such as B0, B1, B2, etc. The output voltage is proportional to the binary inputs, and the binary inputs are connected to the reference voltage, which can be positive or negative. Here in our case, it is plus 5 volt. The binary input that we have, so here B1 is the MSB and B2 is the LSB. The switch positions, they decide the binary word, and the typical value of the feedback resistor which we have is 2R, that is RF is equal to 2R. So this is the typical 2-bit binary R2R ladder DAC diagram. Here we can see that this is an inverting summing amplifier. The inverting summing amplifier, the inverting terminal is connected to R2R and R2R ladder. So here we are considering two binary bits, that is B1 and B2. So there are two combinations of R and 2R. So this is one combination of R and 2R. This is another combination of R and 2R. We have 2R which is connected in the feedback path between the output and the input. And we have another resistor R which is connected at the input terminal here. Over here we can see that this R2R ladder is connected to the switches, that is B1 and B2. B1 is the MSB and B2 is the LSB. The binary switches are either connected to the reference voltage or they are connected to the ground terminal. Here we can also see that IO, that is the output current, is subdivided into I1 and I2, which is flowing in the 2R path. So in this animation, we can see that IO is flowing into, or it is subdivided into I1 and I2. So this is a typical diagram of 2-bit binary R2R ladder DAC. From this diagram, we can see that VO is minus VR into RF upon R in the bracket B1 upon 2 raised to 1 plus B2 upon 2 raised to 2. We will see in the next slide how this comes. So here we have taken the reference voltage as plus 5 volt, RF as 20 kilo ohm, R as 10 kilo ohm. Now here VO, if we substitute the values as B1 0 and B2 0, then the output voltage is 0. If B1 0, B2 1, then it is minus VR by 4. B1 1, B2 0, then this is minus 2 VR by 4. And B1, B2 both 1, then it is minus 3 by 4 into VR. Now these values are when RF and R are equal. In our case, the value of RF and R are different. That is, RF is 20 kilo ohm and R is 10 kilo ohm. So we have output voltage when B1 is 0 and B2 is 0, it is 0. Then when B1 is 1, B2 is 0, it is minus 2.5 volt. Likewise, when B1 0 and B2 1, then VO is minus 5 volt, and when both the binary inputs are 1, then the output voltage is minus 7.5 volt. So these are the values which we have calculated considering our input values. Now we will see the 4-bit binary R2R ladder DAC. In the similar way, we have 4-bit binary R2R ladder DAC. The only difference is, as we have 4 binary bits, that is B1, B2, B3 and B4, there will be 4 combinations of R and 2R. So this is one combination, this is the second combination, this is the third combination, and this is the fourth combination. We have 4 combinations of R to R which are connected to the binary switches. These binary switches are either connected to the reference voltage or they are connected to the ground terminal. In this case, B1 is the MSB and B4 is the LSB. Like in the previous diagram, similarly we have IO which is divided into I1, I2, I3 and I4. In this animation we can see that IO is divided into the currents I1, I2, I3 and I4. 2R is the feedback resistor. Now here what we will do is we will see what is the value of VA when B1 is 1, B2 is 0, B3 is 0 and B4 is 0. So we will find out the voltage at this A terminal. For that, what we need to do is we have connected VR to only this B1 and the rest binary bits are connected to ground. So they are B2, B3 and B4 are 0. If we consider this circuit, here R and 2R are in series, so it will be 2R. 2R and 2R parallel comes out to be R. Again, R plus R will be 2R. 2R 2R parallel combination will give us R. R in series with this R will give us 2R. 2R and 2R will give us R. Again, this R and R are in series, so it will be 2R. So this is the equivalent circuit for finding out VA. Now we will concentrate only on this particular circuit. So it is going to be voltage at the A terminal where we have 2R which is connected to VR and another 2R which is connected to the ground. So voltage at node A, that is VA, is equal to 2R upon 2R plus 2R into VR. So 2R upon 4R into VR, which gives us VR upon 2. Likewise, if we want to find out the value at these terminals, we have to respectively put that bit as at VR and the other bits at ground. So we will get the values, that is VR upon 2 at this terminal, VR upon 4 at this particular terminal, VR upon 8 at this terminal and VR upon 16 at this particular terminal. With this, we can find out the value, that is VO is equal to minus RF upon R into VR, V1 upon 2 plus B2 upon 4 plus B3 upon 8 plus B4 upon 16. We can also write it as VO is equal to minus RF upon R into VR, B1 upon 2 raised to 1 plus B2 upon 2 raised to 2 plus B3 upon 2 raised to 3 and B4 upon 2 raised to 4. The value which is given to us is VR is 5 volt, RF is 20 kilo ohm and R is 10 kilo ohm. So this is a reflection spot wherein some values are given, the binary inputs are given to us and we will find out the output voltage. So B1 is 0, B2 is 1, B3 is 1 and B4 is 0. So what we will do is we will consider this equation and the initial values given to us are this. VO is minus RF upon R, that is 20 kilo ohm upon 10 kilo ohm into 5 volt, and B1 is 0, B2 is 1, B3 is 1 and B4 is 0. You have to put the values and get the answer for VO. I'll pause for a while and till then you find the answer and we will verify it. So the output voltage VO, considering the values which are given to us, The answer is VO is minus 20k upon 10k into 5, 0 upon 2 raised to 1 plus 1 upon 2 raised to 2 plus 1 upon 2 raised to 3 plus 0 upon 2 raised to 4. So the answer that we have is VO is minus 3.75 volt. Likewise, we can find the answers for 0, 0, 0, 0 to 1, 1, 1, 1. These all values we have to put in the equation, that is this equation, and get the answer for this particular values of binary inputs varying from 0, 0, 0, 0 to 1, 1, 1, 1. Next, we see the advantages of R2R ladder DAC over binary weighted register DAC. It contains only two types of registers, that is R and 2R. If more number of bits are present, then only the required R2R sections are included. Like we see that if it was 2-bit, then we had 2R and 2R combinations. Whereas if we have 4 bits, then we will have 4R 2R combinations. Thus, the R2R ladder DAC is more preferable over binary weighted register DAC. Hope you find this video useful. I hope you have understood this concept. Thank you very much.